Hey everybody, today we will do our lab EL325 CMOS of M for junior students in electronics. Well, let's review a little bit. We have our CMOS of M as the circuit in the front, and we have V in negative, V in positive. V source negative and V source positive of the supply. This one we put the supply is the 30 volts, and first we take a look at the slew rate. Let's see, I have for the slew rate. Okay, sorry, I don't have that one. Well, for the slew rate, it means that we want to see how fast the op amp will respond the input signal to output signal of the out. We do the connection of the circuit like this. I have let me get a slew rate open and slew rate. Okay. So the way you connect the circuit, you do a connection V negative short to the V out, and you have a input signal or pulse connected to V in positive. And for the V pulse setup, you can do let's get cursor to the input. For the pulse setup, okay, you put the V initial to be 0 here, V on or amplitude to be 2.5 volt, and T delay, you just close circuit right away, so we don't have delay time. For the rising time, from 0 to hit 2.5 volt or the maximum voltage or amplitude, LTSPICE not allow you to put 0, so you just put small, very small timing. So that's why I put 1 nanosecond, same as T4, and you will see that's going to be your 1 nanosecond. For T on, I just let it to be your on or close switch 2.5. I'm sorry, 5 microseconds, and the period is going to be double of our T on, so that's going to be your 4 microsecond. Okay, and if you want to see the input signal, okay, don't forget to label your wire as the reference. I have slew rate right here. Okay, and I label this one as V out. You simply put the pen on the wire, right click, and you go to label net. So this one become V out as reference, easy to follow. You close it, you click OK, and you put the square under the label V out on your wire. Okay, left click to place and right click to stop. Same as V in and V in plus, V in negative and V in positive. Let's get back to the plot, the slew rate. Let's kill V in negative. So this is your input signal. As you can see, if you want to see it clearly, that's one it's there. You can just put one period, or like about 9 microsecond. And this is your T rise 1 nanosecond, you cannot see. And this from 2.5 to 0, that's the become T fall. And this is your amplitude, 2.5 volt. And your T on become 4 microsecond. See that when you have a 2.5 volt, and your period is going to be 8 microsecond. All right. And now we can take a look at the out. To add more plots on the same plot, you have to go to plot setting menu, and then you go to address. If you use this icon, it's going to remove the previous plot, or you can say one plot at a time. You cannot put multiple plots on the same plot. And this one we're going to see your V out, which is the V in negative, right? With the same V in and V in negative and V out. As you can see here, the op amp will respond your input signal to the output to V out, and that's take time because you have a charging of capacitor. It starts from 0 to 2.5. You can see this one, and that you need to record your slew rate, which is equal to delta V over delta T. And you can pick up, start T, this become T1 when it just hit 0, and then when it's hit 2.5 volt, that's going to be the time T2. So your delta T become delta T2 at this point. On the x-axis you can do the reading. Okay, I can pick up cursor. I just put right here. Now only your cursor 1 active. You want to activate cursor 2, you just double click on V in again. Now your cursor 2 active. And you want to find delta T, and delta V is simply a 2.5 rate. That's what we're looking for, to 0. So what you need to do is you move the cursor. This is cursor number 1. You can just go down to 0. You can notice here I move cursor 1 to the left until it hit 0. Okay, I have this one cursor. This is coordinate X and Y. Horizontal become X, and vertical that's become Y. And I have the voltage just about 0. Okay, and you can move cursor 2 until it hit 2.5 volt. This is 2.5 volt, and the difference of coordinate X, Y become horizontal, or delta T. This is the 530.30 nanosecond, and the vertical you have the voltage different, right? Delta V equal to 2.5 minus 0, and you can find the slew rate by delta V over delta T. So that's mean delta Y is that's vertical, become 2.5 divided by 530 nanosecond. Okay, you do the same thing sorry, for the falling slew rate. Falling, you go down to the green line until it hit about 0. Okay, you can use the right arrow on your keyboard to move. Okay, so that's the best I can do. And now you already have a falling slew rate. Falling become 2.51 divided by 4.01. Okay, and sorry, sometimes you ask for settling time. Settling time is mean like this one is still fluctuate. when it's more stable, you can pick up this one. So this is your settling time. Start from 0 until it's more stable. So about this one. So you can look for the time by moving your cursor 1 or 2, to that point. Okay, and you can read. This is the cursor 1, and your T is the simply you go to cursor 2 to 0. So from 0 to this point, you can find delta T here, and this already given become a 2.68 microsecond. That's settling time. Okay, that's all about slew rate. So by definition, slew rate equal to delta V over delta T. You want the op-amp response your input to output very fast. So your delta T supposed to be very, very small. So something divided by the number close to 0, that's give you the large number. Or the larger number of the slew rate, the better your op-amp will response your input signal. Okay, so that's about slew rate. Let's next for this is for series 1 of the lab EL325 CMOS op-amp, and we will continue our series 2 about the frequency response, which we have both non-inverting connection and inverting connection, or non-inverting op-amp and inverting op-amp. This is the non-inverting op-amp. That means you supply, you connect your V input to V in positive of your op-amp, and for inverting op-amp, you connect your V input to V in negative of your op-amp. Okay, that's the follow for series 1 of the lab EL325, and also the last one equal to be your PSRR, power supply rejection ratio. That means your op-amps should be able to get rid of your noise signal that's come from we supply negative or we supply positive, because op-amp the job is to amplify your signal, right? But if you have the noise coming to we source negative or we source positive, it's not supposed to be amplified. So your V out supposed to be getting smaller. Okay, see you then. Bye.